Hello, everyone, and welcome to the 11th UQM virtual seminar. Today, we are very happy to have Nat Tantivasadakarn and Liujun Zhu. So our first speaker is Nat from Harvard, and he's gonna tell us about Jordan-Wigner dualities for translation-invariant Hamiltonians in any dimension. Nat, please go ahead.
Thank you, Hassan, for giving the opportunity for me to present my work here today. I'm going to be talking about some dualities, Jordan-Wigner dualities, which relate a fermionic system to a spin system. And one of the selling points that I want to talk about today is that fractons has recently been pretty popular these days. And what I'll present in this work is some indication that you can have fractons that are excitations that are immobile, but they could be fermions. So it's quite surprising that you can have fermions, which usually you need to like do some exchange to know that it's a fermion. But in this case, they're fractons also, so you cannot move them. So I would also like to point out some related work that came out at the same time by Wilbur Shirley, which is in the archives below. So let me start by giving some motivation. So in 1D, there are two well-known dualities that we know and love, is the Kramers-Waniya duality and the Jordan-Wigner duality. So in 1D, the Kramers-Waniya duality is saying that if I have a transverse field Ising model and I have this parameter G, then there are two main phases. Here, I stole a picture somewhere from Subir's website. So you can have a region, there's a critical point at 0 temperature where when G is really large, you have a paramagnet, and then when G is small, you have a ferromagnet. And in each case, the excitations are either labeled by charges, or where you flip each spin, or a domain wall for the ferromagnet case. Now, the Kramers-Waniya duality is telling you that basically you can do a duality by swapping X and the Ising term, and brief schematically, that's sort of like flipping it like this, and you can think of the charges as domain walls in the dual picture, and then domain walls as charges. So this gives you a duality. It also gives you the exact value for the critical point in the 1D transverse field model. Also, in the Jordan-Wigner duality, it tells you that a spinless fermion system is dual to an Ising model. And here, the Hamiltonian I've written here is this model, Kitaev's model for this P-wave superconductor. You can have a trivial fermions or this Majorana chain where the endpoints have Majorana 0 modes. And the Jordan-Wigner duality is telling you that by dualizing the fermion parity to the transverse field and this hopping to the Ising, you can realize the trivial phase as a paramagnet and the symmetry broken phase as the Kitaev chain. This is the story in 1D. Now, there have been several generalizations to higher dimensions for both Kramers duality and Jordan-Wigner dualities. So for Kramers-Waniya duality, you can do a similar duality in higher dimensions. For example, in 2D, if I take this 2D transverse Ising model and dualize it, it gives me torque code, and where you can have a ground state which has topological order. Recently, people have also been studying higher form symmetries, where instead of you having a global symmetry, you can have symmetries which are spin flips on closed lower dimensional manifolds that you can wiggle around. And these can give you charges that are higher dimensional excitations, such as loop-like excitation. For example, in 3D, you can have charge excitations, which are like these M loops in the 3D torque code. In terms of related to fractons, there are also the subsystem symmetries where the dimensional symmetries are rigid, and they can be planes or lines in higher dimensions, or they can even be fractal, such as the one studied in, for example, Hooft. So these are all Z2 versions of the Kramers-Wanier duality. It's telling you that if you have a certain transverse field Ising model with a generalized Ising term that has these symmetries, then you can dualize it and you can create topological orders or even fracton orders. On the other hand, the Jordan-Wigner duality has only been, for the higher dimension, has only been studied recently. So this was done in the work by Yuan, Kapustin, Radicevich. And what they did was they considered in, for example, 2 or 3 dimensions, you have fermions on a lattice, and you can bosonize that into a spin system with an unusual gauge theory, and that gauge theory has an anomalous symmetry, and that anomalous symmetry allows excitations to be fermionic. So, for example, in 3+1D, you can have a twisted version of the toric code where the point excitations have fermionic statistics. So this work is to fill the remaining part of this slide, which is to consider fermions that are protected by higher form symmetry or subsystem symmetry. That is, I want fermion parity to be preserved on a lower subdimensional manifolds that could be either movable or it could be rigid, and it could even be fractal. So one of the examples is, for example, if I can obtain a twisted version of Haas code where the excitations live at the endpoints of this fractal shape, but instead of the excitations being bosonic, they are fermionic. And you can similarly obtain these for the fracton models you know and love, this X-cube model, checkerboard model, or these fractal spin liquids. All of these can be done. So to give you a procedure of how this works, let me review how the Kramers-Wanier duality and the Jordan-Wigner duality works in 2 dimensions, and then I'll tell you how to generalize them. So starting with the 2D Kramers-Wanier duality, I have on the hand side, I have a transverse field Ising model. These are my Ising terms on a square lattice. There are 2 types, and then I have a transverse field X, Pauli X, and sitting in each vertex. Now, the formula of doing this Kramers-Wanier duality is pretty simple. It's saying that for each transverse field ZZ, I just need to map it to, for each Ising term ZZ, I need to map it to a transverse field living at the position of that Ising term. Where the Ising terms are defined on each link. So I can map it to a transverse field X living on that link. On the other hand, to preserve the commutation relations, I need to send a transverse field X living on each vertex to a product of Pauli Z operators for each link coming out of that vertex. So here X will be sent to these 4 Z's. And now this Ising term is sent to X. Now actually this model on the right here is also a generalized Ising model. Your Ising term now is this 4-body Z. And it turns out that such a model with this Hamiltonian has higher form symmetry, and in particular a 1-form symmetry. So how do you see that? First, let me say that there are the left-hand side, the global Z2 symmetry, which is a product of X on every side is equal to 1. That's a global spin flip. That actually is enforced from the right-hand side, because on this map, if I take a product of all these vertex operators on every vertex, they all cancel out in product to 1. And that enforces that there has to be a Z2 symmetry, which is the product of X on this side. On the other hand, if I take this Ising term on the left-hand side and product it around a plaquette, or in general, any closed cycle around, say, my manifold, which it could be like a torus, then it gives me a constraint, which is a plaquette term, which is all these x's are equal to 1, or all these x's product around a torus is equal to 1. And you can think of this as a one-form symmetry, which you can think of as a closed E-loop. So this duality here maps a paramagnet, which is X, to a symmetry broken phase under the one-form symmetry. So you can think of it as a topological order because this is like the vertex term and the plaquette term of the toric code. And on the other hand, it maps the symmetry broken phase to X, which is the symmetric phase under this one-form symmetry. And in terms of gauge theory, you can also call it deconfined, this being the deconfined phase, and this is the confined phase, if you like. So now let me do the the Jordan-Wigner duality. I'm gonna do the story is very similar, and I only need to do the following changes. Let me change the transverse field X to fermion parity, and let me replace Pauli's Z operator with either one of these Majorana operators. And what I can do is now I have a 2D list with fermions, where I have a fermion parity, and I have hopping of fermions given by these Majorana operators. And I can do a similarly to spins, where P gets sent to a vertex term of Z's as usual. But now you notice that these Majorana operators, hopping operators, don't need to commute like in the Ising case. So in the Ising case, they were just Z's. But now, since they are gamma and gamma prime, they don't need to commute anymore. It turns out that I can still send this to X living at each link, but I need to add extra Pauli Z's in order to make the commutations work out. So I'm going to explain later how you do that, but for this case, the answer just turns out to be you put this Z over here and this Z over here, and you can check that the commutation relations work out. And this was the work done in this paper down here. Similarly, there are some symmetry constraints that are enforced. So the product of all these vertex term is 1, and this maps to a global fermion parity on this side. On the other hand, there is a funny product of hopping operators and fermion parity, the product to 1 around a plaquette. And this enforces a funny gauge theory over here. So this can be viewed as a plaquette term of the toric code times a vertex term on the toric code. And that's saying that whenever you excite an E particle, a charge, you also need to excite an M particle, flux. So you can only excite the composite of them, which is the emergent fermion, in pairs. So the emergent particles here are instead of bosons, they are now fermions, and under this gauge theory. And you can think of this also as a one-form symmetry, but it's an anomalous one-form symmetry because instead of being closed loops of E particles, now they're closed loops of fermions. Okay. Any questions until now? Okay. So.
Excuse me.
Yes.
The anomalous one-form symmetry means that there is some one-form symmetry cannot be regularized locally on the link. Is that right?
Yeah. So if I have this one-form symmetry is generated by this plaquette term, which has an extra vertex term attached to it, and then this non-local one. So the problem is if I try to couple it to a dynamical, like two-form gauge field, then I cannot do that consistently.
Thank you.
Right. So in general, like what I said, I started with a certain Kramer's Wigner duality. I did this, and I replace X with P, fermion parity, replace Z with Majorana's, and I can do a similar duality to get this Jordan-Wigner duality. And there are a bunch of stuff you can do. I'm just gonna, I just want to show you how various models can be derived. For example, you can obtain twisted versions of Troll's X cube and various other fractals, for example. So let me summarize what is the procedure I want to do. So you can start with, for example, the topological order, or in quantum information speak, Victor's favorite CSS code. What you can do is perform a Kramer's Wigner duality, or what people like to call ungauging, into a transversal Ising model. And once you have this transversal Ising model, you replace X with fermion parity and replace Z with either one of these Majoranas. And what you've done is now you've created a fermion model with a generalized hopping term. And from that, you can do a Jordan-Wigner duality to obtain a twisted version of this stabilizer code, or this topological order that would be different from the original one if your hopping terms like this gamma gamma prime do not commute. So the example I want to give today is, for example, if I start with
in all of these models, when you say duality, do you mean that the two models are identical, or is it that they are identical after you gauge something?
Yes, the duality I'm talking about is a singlet duality. So I'm restricting to the symmetric subsector. You can also do a duality where you minimally couple, but that's not the
you
duality.
Have here, say, any of these dualities, or with the horizontal arrows, does it mean that the model on the left is identical to the model on the right, or not?
All right. So I need to mod out certain symmetries. So yeah. So what I mean here is, for example, I need to mod out subsystem symmetry over here, and then for the X cube, I also need to mod out like the sector where all the fluxes are not allowed.
When you mod out by things like that, you usually also have to add some twisted sectors.
Add some twisted sectors. No, I'm in only one sector though. I'm fixing a boundary condition for both sides, so I don't think I need to add any twisted sector. For example, if this is the 2D code, then I mod out by the magnetic one form symmetry, and then over here I have a Ising model where I mod out by the global Z2 symmetry. And then in the restricted subspace, both these two are dual. Does that answer your question? Hello. If not, then let me continue then. So
I have also a quick
Can I ask a question?
Here. Oh, okay, Matt,
yeah.
Go ahead.
Oh, okay. So in these dualities, is it correct that what's happening is just that the algebra of the terms on your left-hand side is the same as the algebra of the terms on the right-hand side, say on a previous?
Yes. So in the level of operators, yes, that's all you need. And the level of states is more subtle because you need to mod out by certain constraints, like I just mentioned.
Yeah, you may have to restrict to a particular symmetry sector or something like that.
Yes.
Okay,
yes.
So I have a comment on this, which is that there's this old paper by Nusinov and Ortiz where they looked at a lot of examples of this type of thing. They called it bond algebras. And they worked out a lot of examples, maybe not these specific examples, but I think maybe people should look into that paper and maybe cite it when considering?
Yes, yes. I did receive a comment about that, and I did include it.
Okay. All right. Thanks.
Okay. So similarly, you can do this procedure for Haas code. Let me give you an example for how it works out for the X-cube model. So for the usual X-cube model, you have this plaquette-Ising model where on a square lattice you have a transverse field X, but now your Ising terms are plaquettes where there consists of 4 Z operators.
Excuse me.
And, yes.
Sorry, really basic things. A previous slide.
Yes.
How about the vertical arrow? Same question as Nati asked.
Vertical arrow with the left or the right?
It seems like Bosonian operator is mapped to Majorana.
Oh, this is a totally different.
Oh,
this is not related at all. I'm just replacing.
Yeah.
They're not related.
Yeah. Sure. Okay. Thanks.
Can I also ask a question? So for the
Yes.
lower right twisted X-cube model, is that the
Yes.
lattice model with fermionic excitation or with fractonic
Yes.
excitation, or yeah, can you?
It's a spin model where the fractonic excitations are fermions.
I see. Thank you.
Now, I haven't shown that this is actually different from, the ground state is actually different from the X-cube. I think Wilbur in his paper, he argued that actually for the X-cube, the ground states are actually the same in the sense that you can obtain a composite particle X-cube model that has fermionics. But on the other hand, I think we discussed for the twisted Haas code, it should be a different ground state should be different from the usual Haas code. So that still needs to be figured out.
But
Whether the ground
I'm
states
still
are
puzzled
different.
about these 4 models. What's the relation between them? Are these arrows machines that produce new models from old ones, or is that a rewriting of the old model using different variables?
So I can start from the upright, and I can produce a new model on the lower right, which potentially could be a topological order. Going from the left to the right is a duality, but this step here is just has nothing. I'm just replacing bosonic system with a similar fermionic system. It's just like a inspiration, if you would take it that way. So these are not related at all.
Can I ask a question?
Yes.
So maybe I missed it. But so okay, so you replace the Z's with one of the 2 Majoranas. Is there like, so you have to make a choice there, I guess, which side of that link you're gonna put it on?
Yes. But so you have to make a choice there, but in the end, that doesn't quite affect the duality because whether I choose gamma or gamma prime, it only differs by fermion parity. Okay. So I can always replace whatever duality I get. If I replace gamma with gamma prime, I just need to attach this P in. So I just need to attach whatever operator is G on there.
Okay, thanks.
Yeah. Any other questions?
Sorry, so you said the X-cube model and the twisted X-cube models have the same ground state?
Yes.
Do they have the same logical operators as well?
I think that was argued by Wilbur. I'm not sure if he's here, but maybe you could ask. He has an explicit way to show in terms of stabilizers that they're the same set of stabilizers.
Okay.
I'm actually puzzled by that because when you gave the example of Jordan-Wigner duality for Ising model before,
yes,
the other grounds, so in one phase the symmetry is broken, in the other phase the symmetry is not broken. Therefore, in the first phase there are 2 ground states, and in the other.
Oh right, but in terms of states, I need to mod out by the symmetry. So I'm only in this the symmetric. I only choose the symmetric ground state. So if I mod that out,
what do you do when the symmetry is broken?
then there are two ket states, which are like the plus and the minus, and I only choose the plus so that it's symmetric under my symmetry.
No, you cannot. That's the theory is non-local on top of this state.
Yes, yes. I'm restricting to a Hilbert space where yeah, it's no longer a tensor product Hilbert space. In terms of doing the duality, I can only do that in terms of those states.
I don't know what that means. If you have operators, and the operators will take you out of these spaces.
Sorry, what operator?
You
maybe I
have two
should go back
theories,
to this
on the left and on the
this
right.
example here.
For example.
Uh-huh.
So
Here I have a global.
Okay. What I always thought is that when you dualize from the left to the right, the theory either on the left or on the right should be supplemented by another Z2 gauge theory. And then the duality is an exact rewriting of the same theory. You cannot just throw away some state from the Hilbert space and end up with a consistent theory.
Oh, but I'm not adding these extra gauge degrees of freedom, but I'm in terms of states, I'm just modding out by I'm only considering states that are symmetric under, for example, the Z2
but
global
you
Z2.
cannot do that. In the IC, you have operators that are charged under the symmetry. So if you act with them on this.
Oh, I don't have a single Z in my duality here. I only have a double 2Z, so I don't have a charge on the Z2 symmetry. I don't dualize the single Z in this. If you don't mind, I have to go through the X cube example, and then maybe I could take more questions afterward. So for the X cube example, you have this plaquette-Ising model, and what you do X into this cube of 12 Pauli Z's, which are living on the edges. And then for each plaquette term in the dual lattice, you map it to a single Pauli X living on each link. And the constraints of the X cube model come from a product of 4 plaquettes around in the shape shown, and that is equal to 1, and that enforces you have a Pauli X on each vertex like this that is equal to 1. So now let me do an example for the Jordan-Wigner duality for the fermionic case. So I replace X with fermion parity. I replace Z with Majorana's. And it turns out that in addition to this Pauli X over here, I need to supplement it with Pauli Z's living in these positions. And one can check that the algebra of all these operators are still the same. And
all right, so this is not CSS?
Not CSS anymore, yes. So, and then now instead of the constraints here is equal to 1, when I dualize that, this gives me, instead of the vertex term initially, I now have these of Pauli X's, I have this Pauli Z's sitting around outside. So the twisted X cube model instead still has this this cage term here, but now these vertex terms are modified. And now the hopping terms of the X cube model are just these operators, because in order to commute with this constraint, you cannot just have a single Pauli X that excites 4 fractons. So because you need to put these other Pauli Z's in order to make them commute. And because the algebra of this is just 4 Majorana operators, you get something that is different from the usual X cube. So let me demonstrate quickly. So for example, something that doesn't happen in the X cube but happens in this case is I can create 4 fractons out of the vacuum as a square like this, I can move this one into 3 other operators over here. Now I can collapse this back down to this point, and then can annihilate the whole thing. And it turns out that if you do this process, is applying these 2 plaquettes in order, you will get a minus sign, because these are dual to 4 Majorana operators on each plaquette. And the Majorana operator over here has an anti-commutation. So in the cube, you would never get that, but in this twisted x cube case, you would get this minus sign. So this is sort of indication, it's not actual like exchange process, but we're sort of, a bunch of us are sort of working on how to do a legit exchange process to obtain the x cube one. To show that this twisted x cube has fermionic excitations. Let's see, how much time do I have left?
Yeah, probably you should wrap up. So
okay,
yeah.
so let me just say a few words then. That using if you assume translation-invariance, I can prove to you that if you give me any operator and any set of Majorana operators in whatever shape, I can always find you dual Pauli operators which have the same commutation relations. And the basic idea is, suppose I want to replace this P with a bunch of Pauli Z, and like in the Ising case, these two red guys, they commute, but now we need to make them anti-commute, because here these two hopping operators anti-commute, but if I just map them to Pauli X's, they still commute. So what I can do is I can add a Pauli Z here so that these two anti-commute, and by adding them at the right locations, I can obtain the algebra. And to prove in quotes that I can always, is that there are always 2 positions to place the Pauli Z to get the correct anti-commutations, and basically I need to only just pick half of them. And that's sort of related to the fact that given a Hermitian matrix, I can always construct an upper diagonal matrix such that this thing plus its dagger is the original matrix. So that's just sort of hand wavy way that I want to explain it at the moment. And other fun facts that I am able to prove is that these dual spin operators are unique up to a choice-of basis, and it doesn't matter whether I pick, as Kyle mentioned, whether I pick gamma or gamma prime, it doesn't matter. It doesn't affect the duality. And also another fun fact is that whenever I have operators that product to the identity, they're always dual to some symmetry on the other side, and this correspondence is exact, as all the symmetries here will be generated inversely from some set of operators that product to identity. So let me just conclude with some open questions. For example, for these models, how do we obtain fractons? How to exchange fractons to realize that they're fermions? Or when do we know that these twisted models are distinct phases? Is twisted Haas code different phase, in quotes, whatever phase means for fractons from the usual Haas code? In terms of maybe that high energy people might be interested in, is that these fracton models that have symmetries probably have some Hooft anomaly because their excitations are fractons. And how do we generalize concepts such as C-Roth squares or topological actions in the field theory to construct these models? Yes. Let me conclude here, and I'll maybe take other questions if people have.
So I have one question. Did you try applying the duality to non-CSS models and see what you get on the left-hand side? like the corresponding Ising model?
I'm not sure. Well, the thing is, if I start with a non-CSS model, I don't think the terms will commute, right? The Ising terms will commute, right? I'm not sure about that. I need to think.
I mean, you could get some kind of fermionic model instead of like the Ising model. Like you could get the one on the lower left side where you had
Directly, you mean?
Yeah.
Yeah, I haven't done that at all, but that I've heard people try to do that. And
Okay.
that sounds also interesting. Yeah.
What do you mean by fermionic high form or fermionic subsystem?
Yes. So what I mean by that is when people, let's see, when people talk about lattice models with higher form symmetry, that they have spin flips on individual submanifolds. So here I just have a plaquette term of Majorana operators, such that in my fermionic model, I have a fermion parity which is preserved on every in a closed submanifold. I don't know if it gets you a dual. I figured out what the dual model is, but I don't know whether it actually has an anomaly or not. So, for example, in this case, I get a one form gauge point which looks like this, but it's a product of like the vertex terms and the toric code of the 3D toric code, but it could still be anomalous. And I mean, there is a candidate for that, but I don't know if it could be matched with this SPT in 4D. Sure.
Can you go back to the slide where you have 4 different theories related to one another?
Yes.
Yeah, so I'm just curious, can you say again, if you put the upper right corner, if you replace the upper right corner by the 2+1D toric code,
Yes.
what do you get on the lower right?
Right, so for 2+1D, this twisted one is actually the same as the toric code. The ground state is the same, because if I excite a fermion, I can still decompose it as E and M. So in doing this, it is the same. However, if this is the 3D toric code, then this one is a twisted toric code, which the point particle is fermionic, and that one isn't. So it's not always clear when you get a new topological order.
Okay, thank you.
And in the 3D case, you get this extra BB term, like Steenrod square of B in the action of the 3D toric code.
I see. Okay, thank you.
Whereas in 2+1D, it's like just ADA, and that just doesn't give you anything.
I have a question. So for the fermionic, like one form symmetry or something, is that necessarily like non-relativistic, or can it be relativistic? Or
I have no idea, because I don't know whether it's even discussed anywhere. I don't know if it's like you can consider it as a lattice model, but I don't know continuum versions of it. It could be global fermion parity, like and a usual one form, and then you take the diagonal, but I don't know whether that's true or not. Yeah, it would be interesting to look into that.
Thanks.
All right. Let's thank Nat again, and let's move on to the next talk.